Welcome to Chapter 4, in where we're going to talk about instruction set architectures further, right? So in breadth and depth, as this chapter is titled. And so to get us started, just a little bit of an introduction of what we're going to talk about. The previous chapter, where we introduced our ISA concept and really dug into our processor concepts, it represents one of the principal themes of our textbook and of what we're trying to accomplish in this course. The architecture of a microprocessor together with an introduction to its assembly language. So in this chapter, we're going to talk about variations. We're also going to look at the ARM processor architecture in greater depth. And so you can think of this chapter as both broadening and deepening your understanding of ISAs and their applications. And really the purpose here is not to dazzle you with a bewildering array of different processor architectures as if we were teaching the conjugation of like irregular Spanish verbs, but really just to demonstrate the rich variety of instruction set architectures in both the ARM processor and the traditional CISC or CISC processors. And there are really practical reasons for doing this. Because as computer science students later in life, you're going to be exposed to all different types of processors. Some of you may design engine controllers in automobiles. Some of you may write device drivers for applications and workstations. Some of you will write embedded applications for elevators. Right? It's a scary thought that all of these things use the technology that we're talking about, but it's necessary for you as the student to have some understanding of all of the variations possible in ISA design. So some of the things we're going to talk about, right, or some of the reasons why we're going to talk about some of the different architectural features is that we know, hopefully at this point, like in computing, we never stop changing. We never stop inventing. And the techniques that have fallen out of favor sometimes reappear in later generations of a processor, or it's a variation of a theme. It's something that we're building upon. And although we could have probably expanded out this topic forever, we're going to be realistic and cover the things that hopefully are interesting and illustrative of the ways that we can carry out machine level operations. Now, there are some new terms that we specifically want to focus on that are right at the beginning of this chapter. I don't have them up on a slide, but let's just run through some real quick. All right, the stack, which is probably fundamentally the most important data structure in all of computer science. We've talked about the stack before. The stack is super important as we start to talk about how we store subroutines and how we're going to look at our ARM architecture in greater depth. Exceptions and protected modes. Really, computers invariably implement a means of interrupting the normal flow of execution. And sometimes that's because an external device requires attention or a certain type of error, right? In programming, we call these exceptions, occur, and we need the intervention of the operating system. We're not going to get in this in like deep detail, but we are going to talk a little bit about the supervisor mode of how CISC family processors implemented this supervisor and protected modes. MIPS. So it's always instructive to see how others do things. And MIPS is a well-respected RISC or RSIC processor that has a history approximately as long as the ARM processor. And so we'll briefly look at MIPS because it's remarkably similar, and we can kind of look at some differences and trade-offs. Data manipulation, packaging, and bit fields. And so bit field instruction, we're going to talk a little bit about that, where it treats the entire memory space as a contiguous sequence of bits. How we can do things like packing, which is a form of data manipulation. You can read a little bit more about that in the terms section. We talked about memory indirect addressing when we introduced the register, but we're going to talk about this in a little more detail. And then compressed code, which is an unusual feature of an ARM processor, but it's its ability to operate in a 16-bit mode where it runs in a compressed version of its instruction set. You also will hear this called the thumb state, and it's really used to reduce the cost of ARM processor-based embedded systems. And so we're going to look at some code compression techniques. So if you're not familiar with some of these terms, go look either through the terms section or give them a good Google so that you are understanding what we're talking about when we get into those sections. So a quick run through of some history, because honestly, I know sometimes students are like, oh God, why are you teaching me computer history? It's so boring. But we have to understand where we're coming from in order to understand where we are today. Because to be quite honest, today's modern processor architecture and to be able to talk about modern computers requires far more of an understanding of where we came from fundamentally before you can ever wrap your head around what's happening now. And I'm not trying to sound condescending or anything like that. It's just simply an extremely technical topic, which has been developed over several decades. And so, like I said previously, we know in technology and in this case in computer architecture, we are always innovating, we're always changing, we're always focused on the needs of maintaining backward compatibility with previous members of a family, with changing requirements of users, with the fashions and design, with just looking forward of like, this is the technology we need, this is where we're trying to go. And so looking back just a little bit, right, in the 1970s and the early 1980s, progress in commodity microprocessor architectures was driven by both Intel and Motorola. And really what that means is commodity microprocessors is talking about putting them in the home. And so prior to this boom in microprocessor architectures that were actually affordable, businesses had computers, but they were very large and they were very expensive. Computers in the home was this outlandish idea because no one could afford one and no one had the space for one. And then as we have learned that we do with technology, things get smaller and things get more affordable. And so by the mid-1980s, you had this RISC architectures being developed by IBM and Stanford and Berkeley, and they really seemed poised to kill off conventional complex instruction set architectures like the 86K and the 8086 families. And the casual observer could have been forgiven for thinking that the conventional CISC, like the Intel IA32 family, was nearing the end of its life. And we make this mistake all the time, even now, where we look at something and we're like, God, like what possibly could they do? Like, it seems like we're just at the end of the innovation that can be done on this stack. But there was like this revolution, the RISC revolution that abandoned complex instruction formats of those previous processors, threw away convoluted and infrequently used instructions and addressing modes, and employed larger register sets that permitted only two memory-based operations, right? We talked about load and store, right? And load and store were really fundamental. They're key features of RISC machines. And this overlapping and pipelining of our instruction execution is really what made it modern. So as soon as one instruction is read into the computer, the next instruction is fetched from memory. And while the current instruction is being decoded, pipelining kind of thrives on simple, regular instruction formats. It doesn't really go well with the complex, variable-length CISC instruction formats, but Intel had done a remarkable job of taking the IA32 architecture and applying pipelining techniques to the underlying CISC ISA, and Motorola also applied these RISC techniques to its 86K line. And so as we move through the 1980s, we start to see arguments in favor of RISC processors appear to be like just overwhelming. And then we get machines like the MIPS and the Spark. And then we get into really what we would consider the IBM PC and its clones. And this is kind of where we are today. So the IA32 architecture still dominates the market for PCs. Apple abandoned their PowerPC and followed the IA32 path, but now with ARM, right, we are still kind of innovating. So really, Intel did everything that it could to make their IA32 based Pentium architectures as RISC-like as possible. And some companies that cloned these architectures kind of sidestepped this whole debate by constructing processors with RISC cores and RISC instruction sets, but then they executed IA32 instructions by translating them into native RISC code inside the chip. And so you've got just, this is why when I talk about, we can't talk about in absolutes, like you'll very rarely hear me say always or never, because there's just so much differences. There's just too much to talk about. And we just keep expanding. So today, right, the ARM processor, which is a load and store, we use this as our teaching vehicle because it's rather easy to learn. Its assembly language is widely used in a variety of applications, right? If you have an Apple product in your home, you have one. And now we can start to talk about this like in a little further depth. And again, I know sometimes you're like, the history is boring, but we have to know how we got here because it's important to understand where we're going. So let's go back to what I said was probably the most important data structure in all of computer science, which is the stack, right? Great importance. We're going to talk about the stack and data storage. Again, looking at some background issues and then kind of how we're solving these. So high-level language programmers can make use of variables to represent data elements that we can think of as variables, right? These abstract data cells, they have names. We, name them something that we can remember and it's meaningful. The data cell is abstract because it can hold any type of data element defined by the programmer. It's maybe a byte, or it's an array, or it's a record. And as far as the program is concerned, the abstract data cell has all of the properties of a real memory cell, right? We can read to it, it can be written to, we can assign data, and a variable is assigned to the name by the programmer. The process of associating the name with the variable, with the storage location, we call this binding, right? Technical term. And all binding does is connect a name to a variable. So, in addition to its name, a variable has a scope associated with it. Hopefully you learned about this in your programming class, right? What is scope? But the scope of a variable defines the range of its visibility or accessibility inside of a program. So a variable declared within a procedure might be visible only within that procedure and invisible outside of the procedure. And a variable can be accessed inside the procedure, but any attempt to access it from outside would result in an error. So hopefully, we've probably learned scope before, so hopefully this is a little bit of a review. But what this allows us to do is define variables that are visible only in the current or lower level procedures, sometimes called modules, and block structured languages, which if we go back to like the granddaddy of programming languages like Algo 60 or Pascal or C or Ada, which is still used, and then like Java, we still have carried this concept of scope, right? And really what this means is a variable has a lifetime. It has an expiration date. And so we declare variables by assigning names, by reserving storage, and from an assembly language programmer's point of view, variables exist from the moment they're loaded into memory and to the moment when the program stops running, which is a fundamentally different concept to any of these other languages that maybe you've learned. And so in high-level languages, right, a variable is bound to a storage area for a specific period Once the variable's lifetime is expired, the storage area is released, and you can bind it to another variable. And we even have systems built into high-level languages called garbage collectors, reclamation processes that go through and clean up memory for us so that we aren't the ones that are releasing that memory. There's a whole subsystem that's doing that work for you. In assembly programming, that's not how this works. So when we're talking about this idea of storage, right, the process of allocating storage to variables at runtime, we call this dynamic allocation. And it's an important feature in languages like Java, right? So some languages like COBOL and Fortran employ what we call static allocation. And with static allocation, it makes all bindings at compile time. So variables are assigned to storage values when the program is compiled, not when it's ran. Each variable is assigned a location when the program is translated from the high-level language into machine code, and each variable keeps its location in memory until the program is terminated. So it's a very different mindset that we have to think about when we're kind of shifting between high-level languages and maybe the way that we're used to thinking about variables and storage and binding, and what we might do differently with our assembly languages. So let's talk a little bit about how this affects the stack. So when a language uses this dynamic data storage and invokes a procedure, right? We sometimes say invoke. We also use the term activate, right? That's kind of the technical term. We associate each procedure and each invocation of a procedure as an activation record. And the activation record contains all of the information necessary to execute the procedure. You can think about the activation record as a procedure's view of the world. So let's think about languages that support recursion, right? Recursion are methods or functions that call themselves. And so if your language supports recursion and uses dynamic storage, because of the amount of storage required changes as the program is executed, storage has to be allocated at runtime. But then if we start thinking about temporary storage, then things actually change a little bit. So let's look at this figure for a second that shows us the concept of an activation record. There's really two pointers associated with stack frames that you don't want to get confused. So we have the stack pointer, which is sometimes called the SP, right? Just abbreviated SP, and the frame pointer, which is called FP. And so in general, again, no absolutes, all SysEx maintain a hardware stack pointer that's automatically adjusted when things like branches or returns are executed. And so when you are doing those kinds of decision branching and things like that, RISC processors like the ARM don't have an explicit stack pointer. So there's a convention that is used as the ARM's programmers, they maintain that stack pointer, but the stack pointer always points to the top of the stack. And the frame pointer points to the base of the current stack frame. The stack pointer might change during the execution of the current procedure, but the frame pointer will not change. Data in the stack frame may be accessed with respect to either the stack pointer or the stack frame, and by convention is used as a frame pointer in ARM environments, but this could be different in like other environments, so in like the 86K, for example. So and probably the most important point in there is that ARM does not have an explicit stack pointer, and register 13 we've talked about is used as the ARM's programmer maintained stack pointer. So not only does it become our responsibility as the systems developer to write the code that maintains this stack pointer, R11 is used as the frame pointer and R13 is used as the stack pointer. And remember, we looked at that chart of registers, we saw that some were reserved for specific purposes. And But that seems to be like the most important point in there, right? Is programmer maintained. So let's think about this temporary storage a little bit more. Temporary storage is needed when we need to evaluate expressions. So like, let's take a look at this right here. When we have things like the intermediate result, right? A plus B and C minus D, we need to store those somewhere while they're being calculated. And the activation record that we just saw in that previous figure is known as a frame. So we're looking at the whole thing as a frame. After that activation record has been used, executing a return from a procedure deallocates or frees up the storage that's being taken up by the record. So when you are doing your programming and you're thinking about how variables are created and we're calling maybe a procedure and we're doing something that executes an expression like this, really we have to think about how it all works, because really the danger here is that we don't have access to the storage that we think we have access to. We don't have access to the values that we need, or in high level languages sometimes we can actually reach out into memory where we don't have access to, or where the value isn't where we think it is, because it's expired and it's been reallocated or freed up. So if you're writing a procedure, procedures often require a local workspace for these kinds of temporary variables. And the term local here, because we've heard this term before when we talk about like variable scope, sometimes we use this kind of term, but it means that the workspace is private to the procedure and it's never accessed by the calling program or by other subroutines. So if a procedure is to be made reentrant, right, which is a subroutine that can be interrupted and used by the interrupting program without any of its state information being destroyed, right? That's a very specific term if you've never heard this term before. Or if it can be used recursively, its local variables must be bound up not only with the procedure itself, but with the occasion of its use, or otherwise it's not going to have access. And so the reason I'm talking about this is because it's very different from most likely any programming language that you've ever worked with. And this is really what makes writing assembly programming kind of difficult, is we have to think about each time the procedure is called, a new workspace must be assigned to it. And if the procedure is allocated a fixed region of workspace and it's interrupted and called by the interrupt routine, any data in fixed locations are going to be overwritten by the procedure's reuse. And so we have to anticipate this kind of memory usage with our variables and our temporary variables and how we're managing the stack. And so we don't have to do all of this management ourselves. So the stack does provide a mechanism for implementing this dynamic allocation of workspace. There's a couple of concepts here. So we talked about the stack frame and the frame pointer, right? Those are kind of our two fundamental concepts. But the stack frame is a region of temporary storage at the top of the current stack. And I'll show you a figure here that demonstrates how, here, let's just look at the figure. There you go. All right, so let's take a look. Right here, this shows us that the D byte stack frame, right, we can see this right here, is created by moving the stack pointer up by D locations at the start of a subroutine. And throughout this section, we'll assume that the stack pointer grows upwards or up towards low addresses and is always pointing at the item currently at the top of the stack. Some stack points to the next free empty element above the stack, which I don't want you to have to worry about that. So we can see, the state of the stack immediately after a subroutine call, the stack pointer moves back to the return address. And then after the allocation of a stack frame, right, here's our local variables. We basically carve that out. It gets added to the top. And then our stack pointer moves to the top. So because the stack grows towards the low end of memory, the stack pointer is decremented to create a stack frame. So here's an example. We can reserve 100 bytes of memory by using this statement right here. So we sub R13, literal 100, which just says move the stack pointer up by 100 bytes. So remember that the programmer uses R13 of this as the stack pointer by convention, right? That's not a requirement, but this is just what has been considered, I want to say best practice, just how you should do things. Even though it's not enforced, it is what everyone does. Before a return from a subroutine is made, the stack frame must be collapsed by moving the stack pointer down again, and we would do that with add. So in general, operations on the stack frame are balanced. So if you put something on the stack frame, you have to remove it. So let's look at an example. So let's take a look at this code of a procedure. And we'll just point out right away, this might not be the most efficient code, right? So let's walk through. So we are taking our stack pointer and we're moving it up literal 16. We can see the comment, move the stack pointer up by 16 bytes. And then you would have your code, right? We don't really care what's happening in here right now. Maybe we're evaluating an expression. And then we would need to store something. So we're going to store it in R1. And we're going to take it in the frame 8 bytes below the top of the stack, right? So that's R13, 8. And then we'll do some more code. And then we would remove the stack frame because we're done. So we take it back down by its 16 bytes. And then you would be able to move out of this procedure back to wherever you came from. So those temporary variables, whatever we were using on a stack frame, can be accessed using the stack pointer. So this is a good example of how you would do that. So let's look at this figure. The temporary variable, right, can be accessed using the stack pointer. And so in this case, variable XYZ is 12 bytes below the stack pointer. And we can access XYZ via an effective address of our stack pointer and then how many ever bytes we need, in this case 12. Because the stack pointer is free to move as other information is added or removed from the stack, it's better to construct a stack frame with a fixed pointer that is independent of the stack pointer. And so this illustrates a stack frame with a frame pointer. And in this case, the frame pointer points to the bottom of the stack frame, and it's independent from the stack pointer. So if data is pushed onto the stack pointer changes, but the frame pointer remains where it is. Which is honestly maybe it's a little easier for you to understand. I like this solution personally because the variable can now be accessed via the frame pointer, right? So we can use R11 and, right, if we assume that's the frame pointer. And we don't have to worry about if we added more things to the stack that our stack pointer is going to move and that we have to keep track of that. So ARM will not do this for you. This is up to the programmer. ARM lacks a link instruction that creates a stack frame or an unlinked instruction that collapses it. There are other architecture sets that support this, which is why we point out that ARM does not support this. You do have to do things the hard way. So to create a stack frame, you could just push the old link pointer onto the stack and then move it up the stack pointer by how many ever bytes, right? Here's an example of how we would execute that. So in this code, the frame pointer, right, FP, points at the base of the frame and can be used to access local variables in the frame. And by convention, right, register R11 is used as the frame pointer. And at the end of the subroutine, the stack frame can be collapsed. And we would do that with this code right here. And here's where maybe this helps illustrate where the danger comes in, right, of using the stack pointer instead of the frame pointer. So this figure here demonstrates the way in which the stack frame grows instruction by instruction. And so the old frame pointer appears twice, once at the old or previous stack frame on the stack, and once the current stack frame pointing to the base of the stack frame, right? We see it in both places. So in practice, we would use the pre-decrementing multiple store instruction, which is STMFD, right? We see this right here, to push both the link register, which contains the return address, and the frame pointer on the stack. So we're going to look at some code examples because I think at this point, maybe I feel like I've baked your brain a little bit. And I want to make sure that we're kind of really understanding this. It's a very fundamental concept in assembly programming and specifically for ARM programming because this is the way the processor behaves. But it is a very different paradigm from high-level programming that we have to do all of this kind of management. And maybe it just helps us not take for granted the fact that we have high-level systems and compilers and things that do this kind of supervision for us. So let's take a look at this example of an ARM processor stack frame. So this code right here demonstrates how we can set up a stack frame on our ARM processor. We push a register on the stack, call a subroutine, save the frame pointer and link register, create a one-word frame, access the parameter, and then return to the calling point. So let's walk through this. We can kind of just read through the code and look at the comments. So we start with our area. This is our entry. And so starting in our main, we're going to set up R13 as the stack pointer. And we're going to set up R0, right, a dummy parameter. And then we're going to set up a dummy frame pointer. Then we use store to push the parameter into our register 0. Use BL to call our subroutine. Our subroutine is over here. Here's our subroutine. So we push the frame pointer and link register. Frame pointer at the bottom of the frame. Create the stack frame, which is just one word, right? 4 bytes. Get the pushed parameter. Do some kind of dummy operation. Store that. Remove the stack frame, clean it up. Restore the frame pointer, and then return. So we would come back here and retrieve that data. And then we have a loop. So this loop is basically just like an endless loop. It just says, wait here. And then we have some memory set up down here. So here's a visual depiction, right? Initial state of the stack pointer, and then we push the parameter. So now the stack pointer's here. Here's our parameter. And then after we push our LP and LR registers, right? We can see how our stack is moving. Then the state of the stack after creating our 4-byte space. So it moves that stack pointer up 1, but the frame pointer stays where it's at. And then after we do our sequence, right, the LDR, add, and store. Right, and remember we create this 4-byte word at the top of the stack. And then when we push that parameter, when we access that push parameter, it's moved to the new stack frame, and it uses that indirect addressing with the frame pointer. So this is just kind of a snapshot of how this works, right? The output of an ARM processor development system that kind of shows the contents of our registers and the state of the stack after the code's been loaded into the simulator. And so if you wanted to test this out, like you could write this code up and kind of walk through it and see, you know, like what does this look like, and kind of review the memory and everything. Now I realize the simulator program that we're specifically using doesn't really dig into the stack and everything too much. And I think that's fine because this is one of those things, you know I keep saying this. I just want you to kind of understand how this works. We don't need to like do it in depth. You'll have plenty of time later as a computer science student to take a more advanced computer architecture course that builds upon these foundations and really dig into some of these things in more detail. That's not really the purpose of what I'm trying to do here. So let's talk a little bit about another programming concept and kind of how it relates to our stack and assembly programming. As a software developer, you've probably heard the terms by value and by reference, right? We can pass parameters to a procedure by value or by reference. The former, right, by value is a copy of the actual parameter that's transferred, and by reference, the address of the parameter is passed between the program and the procedure or function. And it really just makes a difference code-wise, right? Like what are you trying to accomplish on whether you need to pass a copy so that your procedure, your method, your function, whatever you want to call it, whatever language you're writing it, gets a copy of that value so that it can use that to do its job. But we're not changing it. We're not doing anything to that value. If you did have a procedure that needs to actually modify that value, then you would pass it by reference. And when you pass by reference, you're just passing a pointer to the parameter. Now remember, pointers are just addresses of the memory location of where the value resides. So if the procedure modifies the parameter, it's modified globally because it actually goes to that memory address and changes the value that is present, not in the case of by value where it just gets a copy. And if we change that copy, the original value that we passed it remains unchanged. So if we look at just some sample code, now this is C, so if you're not familiar with C, don't freak out. Hopefully this is pretty easy to read logically. But if we had this swap where we have two integers, A and B, right? And so we have a temp variable, we copy A into our temp, and then our temp, B to A, and then our temp to B, right? We can kind of swap all these values around. This is a different way that we would accomplish the same thing, but notice the difference here. It doesn't actually do what you think it's going to do. In order to determine why this program won't work, we would have to manually cross-compile the code and then trace its behavior and probably try to figure out what's going on here. But if we kind of just didn't load it into memory or read it, right? An optimizing compiler will not reread data from memory that it already has in a register. And so that might sound like a confusing statement, but ultimately what's happening here when we're trying to change out these values, right? So we take like 2 and 3, call swap, And then this statement right here, if you load a literal into memory, read it, and put it somewhere else in memory, it'll do that. But again, an optimizing compiler will not reread data from memory that it already has in a register. It's kind of like the idea of a cache, right? Most of us probably understand a cache. We have to clear them in our browsers all the time. It helps our web-based environments go faster to not have to constantly reload pages that we've been to before. And that is essentially the same idea of what an optimizing compiler is trying to do. So the structure of the program, right? We would have to set up, because right now these are read and they're pushed onto the stack by value, and then the function swap is called. Then a second stack frame is set up to hold the temporary variable while the two values are being swapped, and then the swap takes place using both parameters on the stack and the temporary variable in the current stack frame. And then finally the stack frame in the swap is removed and the return back to main is made. And on returning back to main, its stack frame is collapsed and the program is halted. Maybe that helps you understand where I'm coming from. And this is why, as a software developer, this kind of code evaluation is important, because otherwise you might debug this and not fully understand why it's not working the way that you expect it to work. And really, when we consider that any high-level code we write is ultimately going to be translated down into our assembly code, if we understand these fundamental concepts of how things actually work at kind of this bare metal, low-level way, it makes us better developers. It makes us better writers of code, readers of code, and debuggers of code. So let's walk through what this actually looks like, this code right here, when it's broken down into assembly. It's long, all right? So stick with me here for a second. So we start with our entry. We're going to set up our stack pointer and our frame pointer, and then we have our function main. Here's our swap with our parameters. Parameter A is at frame pointer plus 4. Parameter B is at frame pointer plus 8. And then we have a variable temp at frame pointer minus 4. Here's our swap. And like I said, it's kind of long. So let's observe kind of how this works, right? So we create our stack frame. We decrement our stack pointer. We push the frame pointer on the stack. The frame pointer points using the move at the base. Then we use the sub to move the stack pointer up 4 bytes for our temp. Here's our temp. We assign A to temp. Then we get the parameter A from the stack, right? We copy A to the temp, right? So that's this instruction. Then B equals A. We get the parameter B from the stack, and we copy B to A. And then temp into B takes this temp from the stack frame and copies temp to B. And then we collapse the stack frame created for the swap. And we restore the stack pointer. And we move the stack pointer down 4 bytes, and we return by loading our link register into the PC. Right? And that would take us back to our main. So as you can see, right, here's the point. When a return is made, the stack frame is collapsed and the effect of the swap is lost. The variables in the calling environment are not affected. And if you want to walk through this visually, there's one of these figures that walk through the whole swap operation so that you can kind of see how this works if walking through the code wasn't helpful. So really what it comes down to is by not understanding, whoever this programmer was, right, for this example, by not understanding how stack frames work and what their effect would be on these variables, the parameters are only swapped within the function because they're passed by value and are thus copies of the variables in main. The parameters are swapped only in the function swap stack frame, which is collapsed when we exit the swap, and the variables in main remain unchanged. So instead, we must swap the variables in the calling function, which probably isn't what we want. So how would we fix this? And this is where the pass by reference comes in. Now, before we talk about pass by reference, there's one thing I want to talk about, because if you're not familiar with the concept of a pointer, we need to talk about pointers first. So here's our C code. Now you'll notice some syntactic differences, most likely all of the asterisks. And so our book talks a little bit about pointers in C. This is C code. C, for the most part, is easy to read if you're familiar with like C# or Java. If you've never written like a more procedural language like this, or I'm sorry, a less procedural language like this, like maybe you've written Python or JavaScript or something, maybe this feels a little weird, but pointers they're a pretty fundamental concept in most high-level languages, and they are a variable, but they don't contain a value, they contain a memory address. So you can write programs in some languages without having to ever understand the nature of pointers, but in C, like C is pretty famous for being pointer-oriented, and in C, you have to indicate explicitly that a variable is a pointer by prefixing it with an asterisk. Now, in some languages, we have keywords to specifically denote that we want to pass by reference, because the default is typically by value. I believe in Java and in C#, it's ref. You can tell me if I'm wrong, but I know that that's true in C#. I don't write a lot of Java. And most languages have a way to indicate that you want to pass the value by reference, which creates a pointer, but doesn't really explicitly talk about it like it's a pointer. But that is essentially what's happening under the hood. And so if we look at this code, right, the operator asterisk indicates, like in this case, when we put it in front of like A and B, that the int indicates that the pointer is pointing at an address that contains an integer. And in this case, C requires us to declare pointers to be of the same type as the data that they're going to access, because the compiler needs to know the size of each object it's being pointed at. So the data type is still important, although the variable that we're actually talking about only contains a memory address. So when you put an asterisk in front of a pointer, you're said to be dereferencing the pointer, which is accessing the data being pointed at. And so having created the pointer, you have to initialize it. So you can see, we're setting up these values here. They're being passed in as parameters, but we're creating pointers instead and binding those to our A and B respectively. So what this changes down here in our function code, right, is so temp equals pointer A assigns the value pointed at by pointer A to an integer variable temp, and pointer A equals pointer B, or pointer B equals temp, right? We're just pointing to locations pointed at by pointer B into pointer A. So instead of changing copies, we're literally saying whatever this is being pointed at is going to go into whatever this is being pointed at. So we're not talking about writing copies. We're literally going to memory addresses and changing values. And so this changes, if we go back to the assembly, right, the beginning of this still looks the same, but our swap looks a little different. So let's get in, here we go. So our pointer A, right, we get the address of a parameter of A, and we get the value of parameter of A, and we store the parameter A in a temp, in the stack frame, and we get the address of parameter B, and we get the value of parameter B, and we store parameter B in parameter A. And so when the stack frame is collapsed and we restore the stack pointer, we restore the old frame pointer from the stack, and we move the stack pointer down 4 bytes, and we return the loading link register contents into the PC. We didn't lose anything because we literally went to those memory addresses and put those values there instead of putting them on the stack frame. And so when the stack frame gets collapsed, we don't care. We're done. So if you want to look at the visual form of this, again, we have the figure that kind of shows us how we move through the state of the stack, passing values to the subroutine by reference. And so then, of course, we can see that after pushing the parameter addresses and then the state of the stack after the subroutine call, and the stack frame is created. And we have all of these new addresses. And again, the whole point is when we're in that procedure, we're actually going to the addresses and making the changes instead of putting those changes in the stack frame. So when we collapse the stack frame, we don't lose anything. And that is fundamentally how by value and by reference works, and why it's important for you to understand that as a programmer. Like, these are extremely fundamental topics, and no matter what language you're using, most likely supports this in some way if it's a compiled language. And it's important to understand also what is the default mode of the language that you're using, because there are a few who default to by reference, which can be a little dangerous, right? Like, you're changing values that you don't expect to change, and when you get back to your calling procedure, you might have expected they passed by value. And so this is one of those things, again, it depends on what you're trying to accomplish, whether passing by value or by reference is the mode that you should use. But understanding how it actually works, this is what we're talking about. This is the whole point of the stack frame. So I know that in terms of these lectures so far, this one's running a little long, but I really only have one more topic that I want to talk about, which is privileged modes and exceptions. And then that's going to wrap us up for chapter 4. So instead of breaking this one up into pieces, I figured let's just take it all at one go. If you needed a break, like, this is a good place for a break. And then we talk about privileged modes, but I promise it won't go on for much longer. But just to make sure that we're talking about the same thing, right? Exceptions in programming are like subroutines, but they're jammed into the code at runtime. And it's because something has happened, right? Exceptions use a very similar call and return mechanism that we see in subroutines, but the call address is typically supplied by the hardware. Now, this isn't always true, but in the terms of assembly programming, this is true. But when we're working with assembly, right, a processor decodes the exception type. It reads a pointer that indicates the start of the exception handling routine. And some processors save the current status word as well as the return address, because an exception shouldn't alter the processor's status. And this is really how, like, as you are using your operating system and as you're using your computer, like, if a program messes up and has an exception, it's up to the programmer to have written that exception handling method, right? How do you want the program to proceed, or does it just crash, or is the exception unhandled? And that's not good. But then the program just closes. Your operating system kind of handles the whole, like, oops, something went wrong. Let's just clean all this up and do whatever. If your operating system creates an exception, there's a lot of code built into, like, modern Windows and Mac operating systems that really help us kind of survive an exception. But you've probably had, like, blue screens and stuff happen where Windows just suffered such a catastrophic exception, either on software side because something horrible happened and the computer just couldn't continue, so it had to shut down and clean up and restart. But you can also have exceptions at the hardware level. So, like, maybe you have a graphics card that's not behaving properly, or a stick of RAM going out, and it will cause exceptions sometimes to look like they're happening from the operating system. You're still getting blue screens, but we get these error codes that tell us, like, maybe this is a hardware fault, or page faults due to memory access errors, operating system calls, illegal instructions, divide by zero exceptions, right? These are all things needed to be handled by your operating system software. And if it can't, that's where those kinds of errors come from. And so from an assembly standpoint, our processors change their operating mode when an exception occurs. And so this mode, we call these privileged modes, or where certain operations are not allowed because we're in a state of exception. Something has happened. We need to handle that before we can continue normal operations. And so we're going to talk a little bit about these privileged modes and exceptions so that we can understand these in a little more detail. So interrupts and exceptions are events that force the computer to stop normal processing and invoke a program called an exception handler. Normally, this is part of your operating system, and it's specifically designed to deal with the exception. So whether that's capturing and trapping that exception information, like error codes and messages and logging and things like that, so that we can troubleshoot and pinpoint the error, cleaning up temporary files, resetting systems, writing registry values, everything that it needs to recover. So in this type of exceptions, when they're raised in response to an internal hardware or software error, like maybe by a peripheral, programmers can use software interrupt instructions to call operating system functions such as input or output operations. And so in ARM, let's take a look at this table. At any moment, like in an instant, an ARM processor is operating in one of these modes. So we have the 5 low order bits of the CPSR that define the current mode. And so the normal operating mode is the user mode. So the switch between modes takes place whenever an interrupt or an exception occurs, and each of these modes has kind of its own saved program status register that is used to hold the current CPSR when the exception occurs. So that these exception switches in new registers, like register 13 and 14, they're indicated by these names in here in the table. So our registers change based on the type of mode that we are using. And this figure here shows the registers where those in dark blue are banked and are associated with like specific operating modes. And you can see here that registers 13 and 14 are replicated in each of the operating modes. So for example, if a supervisor exception occurs, the new registers 13 and 14 are called with those status codes R13 SVC, R14 SVC, right, respectively. So when writing ARM processor code, these registers, R13 SVC, R14 SVC, are still written as R13 and R14, but it's important to remember that when we switch to the supervisor mode, the user mode values of R13 and R14 are no longer available. So these are entirely kind of independent banks of registers named the same thing, but ultimately, respectively, hold different values. So this mechanism means the programmer does not have to save R13, R14 each time an exception occurs. I say that unless it's a nested exception. But they're generated by both internal and external events. So an external event is like an interrupt request, right? We call that an IRQ. And so when an IRQ happens, like a fast interrupt request, the reset and things like page fault, then internal exceptions would be things like software interrupts and undefined instructions. So when these exceptions occur, the ARM processor completes the current instruction unless the current instruction itself is the cause of the exception, and then it enters into its exception processing mode. And so here's kind of the sequence of events. So the operating mode is changed to the mode corresponding to the exception. So for example, we had an interrupt request. We're going to select IRQ mode. And then, and I say we, the processor, it just does it. We are not doing anything. The address of the instruction following the point at which the exception occurred is copied into register 14. So the exception is treated as a type of subroutine call, and the return address is preserved in that link register. Basically, so if we can recover, we know where to go. The current value of the current status processor status register, that CPSR, is saved in that SPSR IQ. Or I'm sorry, no. The CPSR is saved in the SPSR in the new mode. Oof, that's hard to say. So if your exception is an interrupt request, CPSR gets saved in SPSR IRQ, right? It's written here. I'm going to stop trying to say it. It's like a tongue twister. It is necessary to save the current processor status because an exception must not be allowed to modify the processor status, right? We want to save the current status so that we can handle the exception and then resume if possible. So our interrupt requests are then disabled by setting bit 7 of the CPSR. And if the current exception is a fast interrupt request, then further FIQ exceptions are disabled by setting bit 6. Right? So each location in the exception table contains an instruction that is executed first in the exception handling routine. This instruction is normally a branch operation, so like be my handler, like whatever it is named. And we would load the program counter with the address of the corresponding current exception handler. So we can look at this table, which defines the memory locations accessed by the ARM processor's exceptions. So each memory location contains the first instruction of the appropriate exception handlers, and this implies, of course, that the table should be in read-only memory, right? And so you'll note in here that the vector addresses, right? Take a look at these. They're non-contiguous because the entry at memory location 14 is missing. So when the ARM processor was first introduced, it's like a fun tidbit. The location was used by the misaligned word exception. And later versions of the ARM processor can handle misaligned addresses without causing or calling an exception handler. So there used to be an additional item in here, but now we just took it out. So after the exception has been dealt with by a suitable handler, it's necessary to return to the point at which the exception was called, unless it's fatal. Right? A fatal exception is where a return is no longer possible. We cannot continue. Usually a restart of some sort has to take place. So we return from the exception. We take the information that defines the pre-exception mode and we basically restore it. So the program counter, the CPSR, it's not as trivial as it seems. So if you restore the PC first, you're still in exception handling mode. If you restore the processor status first, you're no longer within the exception handling routine, and there's no way in which you can restore the CPSR. So you can't use like a normal sequence of operations to return from an exception because it involves a change in operating mode. And two different exception return mechanisms are provided. So let's talk about that for a second. One is for the case in which the return address has been stored in the banked R14, and the other is for the case in which the return address has been pushed onto the stack. So the return mechanism depends on the type of exception being handled. So if you're returning from an exception where the return address is in the link register, you can execute some instructions where your moves and subs are special versions of the normal instruction used. Here we can take a look at this in the table. To modify the value of the PC when returning from like an IRQ or FIQ or a data abort. In the former case, the program counter has to be wound back by 4. And in the latter case, the program counter has to be wound back by 8 in order to repeat the instruction that faulted. So it's a little different depending on what we're doing in order to get us back to the state that we want to be in. And just like an extra special note here, the caret symbol, I don't know if most people realize that that's what this is called, right? That's the little guy on the 6 key called the caret, not like the vegetable. I know how do I get the closed captioning to spell this right? I guess if I just spell it out. It's C-A-R-E-T. Does that work? Caret. There we go. Anyway, this symbol, after the register list, so like if you see it like this or you use it like this, indicates that the CPSR is to be restored at the same time the program counter is restored. So the program counter was not modified at the point at which it was restored. You have to modify the program counter before you stack it. And so this is where, you start to think, oh, like assembly programming, this seems pretty straightforward. And then you get into these kinds of topics and you realize it's actually quite complex. And so there's a lot that goes into handling exceptions and different types of supervisor modes. Of course, we're just specifically talking about the ARM processor. Each processor kind of has its, or at least family, adopts its own kind of interesting approach to exception handling. There's a lot going on in here. But this is the end of what we're going to talk about in Chapter 4. Now, there is a lot more in Chapter 4 about like MIPS and data processing instructions. I definitely think that you should read it. Data processing and data movement. If you really want to get into like indivisible exchange information and double precision shifting and bounds testing and other kind of cool topics, by all means, read the chapter. But this is the end of what I'm going to lecture on because I consider it to be like the most important points of Chapter 4. And so I hope you've enjoyed this. Sorry it was a little longer than usual, but thank you for sticking in there with me. And I hope you enjoyed.